computer, and then I'll convert it. And I'm going to start with a model that you might have seen before last time. Okay, so this is about a team of graphic designers that need to perform a project. And they need to be assigned an amount of time, not the same, because some are senior designers, they'll be assigned for more time, and one is a junior designer that will be assigned to less amount of time. And the total amount of the project duration is 150 hours estimated. And Lisa, the senior designer, who is also the project head, will be assigned to at least 40% of the time of the senior time. Sarah, who is a junior designer, will be assigned at least 50% of the total time. And one reason why you put such a constraint by management is that if you don't, that she might not be assigned at all, only that will be surprised later. And Sarah, on the other hand, will not be assigned more than 25% of the senior times. Then Lisa, who is experienced and is involved with other projects in the company, cannot dedicate more than 50 hours to this current project. And finally, there are the wages for each one of the three. As you see, Sarah is earning much less. So the problem here is how many hours to assign to each one of these three workers such that the total cost is minimized and all the other restrictions are met. You can understand that if you have a huge project with hundreds of workers, then you don't go one by one, you go by groups. And you are dedicating time to the group. And in order to either maximize profit, either to minimize the time you finish the project, either to minimize the cost of the project. So there are a variety of angles to exactly the same problem. It's all about management. It's a team management. So it's a huge thing in optimization, in running project in general. So the model, since we did linear programming before, I think I'll go over how to set it up, the technique faster, and then I'll go to Excel. I go to the actual Excel file, we run the Excel, get the solution. I want to remind you how to enter an Excel model on a spreadsheet, and then how to translate it into a solver model. So what you see here, the variables that you start with are called Lisa, David, and Sarah, which are the people there, but these ones are the hours assigned to each one of them. And the total cost of this is the objective function to be minimized. 30 is the wages for Lisa, 25 David, 18 Sarah. So that's the total cost that this project will cost you. The total time is, and if you remember last time I showed to you, you add the numbers 1 because that's how it will going to go to the spreadsheet below. So I added it here just for your convenience. And this has to be 150 hours. You understand that on the left here, we calculate hours because these three variables are defined as hours. And the Lisa hours is at least 40% of the total senior hours. So you see Lisa 1 and 0, 0 on David and Sarah. But this is at least 40% of the sum of Lisa and David. See, it's the hour for Lisa plus the hours of David. And Sarah has to have at least 15%. So the one is here, 0 on the other two. So Sarah has to be at least 15% of the total time. But the total time is 150. because I forced it on the first constraint. I said equal to. So I wrote it here as Lisa plus David plus Sarah, just to show to you that it can be done. And many times you have to write it. In this particular problem, I could write 150. I could do 1.15 times 150 that represents the total time anyway. But this is only because I know for sure that all the 150 hours are going to be used. At the same time, Sarah has a maximum amount allowed, and this is 25% of the senior time. And finally, Lisa, so the one is here with 2 zeros, cannot exceed 50 hours. And this is the model, okay? Then you go to Excel and translate this into an Excel spreadsheet. I'll go to Excel now and not only look at the model, also run the model, okay? So it will be, okay, just a moment. Just a moment. I may need to look for it for a second. Let me see. No, it's not this one. This one we'll see later. So I'll have to. Yeah, see, it's opened and still doesn't show here. Okay, just a moment. Yeah, this is the one that I missed. Okay. As you see, this is the linear program of the problem, and also has a solution that I want to delete at this moment and rerun it so that we see it from the beginning. So you see, it's the same model. The only thing that is missing here is 0 here, 0 here. I just didn't write the zeros, but I said last time, if you don't write anything, it's a 0. The second thing I want to mention to you is how do you write these 3 constraints here? These are constraints that are written in a non-standard manner because variables are included in the right-hand side of the constraint. This is the left-hand side, and this is the right-hand side. So instead of writing 0.4 times Lisa plus David, that has no meaning for Excel, you write 0.4 times M2 plus N2. And why is it so? M2 and N2 are the 2 cells where the Lisa variable value is contained. I'm going to instruct Solver to do that. So I want on the right-hand side to have the 40% of the senior time, and therefore it's M2 plus N2. Second is the next one. So now it's 15% of the total time. I used sum instead of M2 plus N2 plus O2 just to demonstrate it. This is good idea to use when you have many variables. So instead of typing plus, 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 you just do sum. So it's very common in linear programming to use the function sum. Also, I could place here 0.15 times 150, and it will be as good. And the last one here, I'm using sum again on M2 times plus N2, see, just as a demonstration. This is one thing I wanted to indicate to you. And the second is to remind you about sum product. Sum product is a function, is an Excel function that does the product of pairs of numbers in 2 different arrays And after you calculate the multiplication, you add them. So it's a shortcut to do the function 30 times Lisa plus 25 times David plus 18 times Sarah. Instead of doing that, you write some product and you enter here Lisa through Sarah, and then 30 through 18 here, and you get the result. The thing to remember is that you are going to use this sum product in the first constraint and the second, in all the constraints on the left-hand side. So you want all of them be multiplying their own value of the variables here, and also here, and also from here, all of them. And therefore, when you copy and paste this sum product down the column here, you want it, remember that this needs to belong to all the sum products. Therefore, here you put them in dollar signs. So the way to do it, I'm reminding you guys, you enter M2 through O2 by selecting it, then you press on the keyboard the key F4, and this will enter the dollar sign. If you forget to do that, and you want to do it later, you cannot. You will have then to highlight yourself with the mouse the cells you want dollar sign in, and then you can press F4. So my suggestion is press F4 right after selecting the variables. And then you put a comma, see a comma here. And you enter the second array, and it will calculate the profits. If I put values here, arbitrary values, you see a value here. What you do then, place the cursor here, and then left click and drag. This is one way to do it. Or place it here and left click twice, and it will do it automatically. Now you have on the left the cost function, which is the objective, plus all the left-hand side that needs to be either equal to 150 or greater than whatever, or greater than whatever, or less than 50. So now you can use this for Solver. Not that you can use it. This is the only way Solver will understand something. Solver needs you to enter here a function, a function, a function. Select the way you want to enter the function, but Solver needs to see a cell with a function on the left and a value or a function on the right. So in this constraint, for example, it sees a function on the left that should be greater than or equal to a function on the right. That's legitimate, but this is what Solver needs. I'm going to Solver now. So you have to click on data. I did already, and go to Solver. You have the model already, okay? So you have the model. So the objective function is P3. If you leave your cursor on P3 before you go to Solver, you don't have to enter here anything. It will already be selected. If you leave your cursor somewhere else and you go to Solver, then something else will be here. So be careful that you have the objective function entered here. Then it's a min, not max, it's a min. And here you just click, and then you select M2, N2, and O2. That's what you want to see here. Now comes the constraints. I'll put it here. So the constraints, you click add, and you enter the first constraint. What does it mean, enter the constraint? You have a left-hand side in relation to the right-hand side. In our case, the left-hand side is P4. So you enter P4. Now, where do you enter it? Okay, let me do it again. So you click add, and this is where you enter. I can enter it again. P4 on the left, and then you select equal to, and R4 on the right. This is a constraint. If you click OK, you will see it. If you want to add more constraint, you click Add. Here's another example. So now I'm showing to you something I didn't show last time. Because you have two constraints written under one another with the same sign, you can now enter them as a group. So here's what you do. You select the two left-hand sides together, and then you change it to greater than or equal to, and it's waiting for the right-hand side, the two right-hand sides together. See? Then you'll do the same here because both are less than or equal to, so the two left-hand sides are less than or equal to the two right-hand sides. Let me go OK here, and you see, I have this one twice because I entered it second time, and I have this one twice, so I'll delete it. Actually, if I left it, nothing happens. It will just relate to one of them. That's all. So we enter the model, make sure it is non-negative, and that the simplex algorithm is the one selected out of 3 algorithms here. See, 3 algorithms. Select simplex. And now when you solve it, you got a solution. Since I want to create sensitivity report, I'll click sensitivity here. See? When you click sensitivity report and you click OK, what it does, near the tab where you are on, it will place on the left a sensitivity report. It's number 2 because in my last presentation, I already did it and didn't delete it. It's the same report, exactly. So it numbers in number 2, and this is how it looks. So we'll go to PowerPoint to do some questioning here. What the solution is telling you is that this is the number of hours be assigned to each one of the employees, and this is what it will cost to the company. That's the minimum possible cost. And as you see, on the left, you used exactly 150 hours. On the right, Lisa is assigned to exactly 40% of the senior hours. What are the senior hours? Let's see, 48 and 70, 120, 40%, 48. So Lisa is assigned to exactly 40% of the senior hours. And what's interesting is Sarah. She should be assigned to at least 50% of the total hours. We have 150 hours. 15% is 22 and a half. She is assigned to 30. So they like her. The company wants her to work more. No wonder she is being paid so little. Indeed, why did it stop at 30? Because Sarah cannot be assigned to more than 25% of the senior hours, which is 120 hours. So 25% is exactly 30 hours. So that's the maximum you could assign her to. Tells you, by the way, that if you relax this constraint and allow her to work for more, she will be assigned to more, and the company can then save money. So we'll talk about this aspect as we do sensitivity analysis. And what's interesting here that Lisa, that is the prime person there, she is the senior. She is not even assigned to all the 50 hours, only to 48. So yes, she is an expert, but it's very expensive for the company. And if they can do with less than the maximum allowed for her, they will. Okay, so this is the linear programming solution. And what I want to do now is go back to the PowerPoint, because there where I placed the sensitivity analysis questions. So it will be a good reminder for you. Okay, going back to the PowerPoint. And this, so this is the model. This is the Excel model. Here is the sensitivity report. Remember from our last meeting, for those who participated, that based on the graphical presentation that I made there, we could conclude that there are two ranges that result from this analysis. One is for the objective coefficients, summarized here, and one is for the constraints right-hand side, summarized here. So I'm focusing first on the objective coefficients, and those coefficients, each one individually has its own range of optimality. The range of optimality for an objective coefficient is a range where the value of the coefficient can move within such that the optimal solution that is mentioned here is not changing. In other words, let's assume that Sarah started to earn $20 an hour. That's more expensive for the company. You will still assign her to 30 hours. If she assigned to $25, that's much more expensive. That's just like David now. She will still be assigned to 30 hours. When would it change? If she will be assigned to more than 27 hours. So there is a allowable increase in this coefficient for the solution to remain unchanged, $9 for Sarah. There is $5 increase allowed for David. And now comes Sarah. So this is the first question that I am posing just under this. Here I'm summarizing for you what the allowable increase and allowable decrease means. How much an objective coefficient can increase and how much it can decrease the objective coefficient without changing the optimal solution that is mentioned here. Okay? So the first question, Lisa is earning right now $30 an hour. Suppose her wages increases by 10%. This is $3 increase. So you ask yourself, what is changing? This 30, it's adding $3. You immediately look at the allowable increase. The allowable increase is infinity. This is the infinity value. So no matter how much Lisa is going to earn, the current optimal solution remains unchanged. Listen, if she is earning more, she's becoming more and more expensive for the company. The tendency is to reduce her hours if you want to save overall cost. Problem is there are constraints that don't let you do that. She is probably already at the minimum. If you reduce hour here and you want to spend 150 hours, another person needs to get these hours. Maybe Sarah. No, Sarah cannot. She already at 30 hours. She cannot be added anything. So the solution will not change no matter how more expensive Lisa becomes, because the allowable increase is infinite. And what can we learn from this? Another thing is that we can use the current optimal solution that is not changing as Lisa is earning more in order to recalculate the new objective value, which is the new total cost. So the new total cost, if indeed she is earning $3 more, is due to, hey, she earning $3 more an hour. The others didn't change, and the amount of time assigned to them are not changing because the optimal solution as a whole remain unchanged. So $72 of David and 30 hours of Sarah remain the same cost to the total. Well, the only thing changes here is the 48 hours by Lisa, and by how much it changed? $3 an hour. So without the need to rerun the model, you can anticipate what will be the total cost. It's the old total cost, minimum, right here, plus $3 added times 48, which is Lisa's additional contribution. So that's how you can use the range of optimality and the fact that the optimal solution remains the same. Here's an example number 2. So now David is earning $25 an hour. We know that. It's here. But suppose his wages are dropping by 10%. Hey, based on the corona, maybe some workers are taking a pay cut. Who knows? So it's decreasing by 10%, and this translates to $2.50 decrease per hour. What are we going to assign more hours to David because he's now less expensive for the company? The answer is based on the observation that the allowable decrease now is 15. 2.5 decrease is falling inside the range of optimality. So the optimal solution remains unchanged. He still is earning, be assigned 72 hours. So the only change in the total cost will be due to him costing $2.50 less per hour to the company. So how much less the total project will cost is the previous cost, but less 2.5 times 72 hours. So we use the same concept in here. And now I'm moving to the next part of the sensitivity report that has to do with the constraints. Constraints are changing, one constraint at a time. Okay. So I want to make a comment here. You see the 0 here. This 0 should have been 50. That's the right-hand side. This is Lisa not be assigned to more than 50 hours. There are algebraic reasons why you see 0 here, but this is not 0, it's 50. So it should not confuse you. There is a range of feasibility that I'm going to talk about here that is related to this value. It relates to the value 50. It's an exception. Those zeros that you see here are because of very good algebraic reason that solver is placing 0 here, but we can look at how the original constraint looked, and I'm going to do it, and you can do the sensitivity analysis with no interruption. So first of all, these two allowable increase and allowable decrease relates to those right-hand sides of these constraints. It's related to how much those values on the right-hand side can change without affecting the shadow price. Let me remind you what the shadow price is. The shadow price is defined as the change in the objective value per 1 unit increase of the constraint right-hand side. In this constraint, for example, 25.2 is the change in the total cost, so it's coming in dollars, per 1 unit increase in this constraint. 150 is the hours available for this, for the completion of this project. If you get 1 more hour, or if you need 1 more hour in order to finish the project, this will cost the company $25.2 more. That's because you have now to assign these people to more time, and this will cost you $25.20 more. Then, if you look at the last constraint, the number 50 should be written here. 50 hours is the maximum amount that Lisa should be assigned to. So if you allow her to be assigned to 1 hour more, 51 hours, nothing will happen to the total cost because the shadow price is 0. So if you allow her to work 51 hours, this will not have any effect on the total cost. And if it will not have any effect on the total cost, then the current solution remains optimal. In here, back to the first constraint. When you added 1 hour to the project, you have now to feed all those workers with 151 hours. So 150 hours is infeasible. But once you have to feed them with 1 hour more, this solution that amounts to 150 needs to change. So when you have a shadow price involved in an optimal solution and you make a change in the right-hand side, the optimal solution does not remain the same. This is not as the change that you made in the coefficients where the solution remained the same. What remains the same when you allow a constraint to change are the shadow prices. And that's important because now you can use them to re-evaluate the total cost. But the optimal solution must change when you have a shadow price. When it is not having a shadow price like here, then the solution remains the same. So let's now go over these details. It is now estimated that the project will take 155 hours. So the first estimate have changed. Management realized that they were too optimistic. The project will take 155 hours. Management want to know how much more they are going to pay. Well, the number changing in our model is the number 150. And this is a right-hand side of a constraint. It becomes 155. This means an increase of 5 hours. These 5 hours will not change our shadow price because the allowable increase is $6.25. Which means until the project takes 156 hours and 25, 156 and 25 hours, until then, the shadow price remains 25.2. So every additional hour added to the duration of the project will cost $25.20. Therefore, 5 hours added to the project will add to the total cost 25.2 per hour times 5. The point that I'm making here is you can use this value of 25 and 20 cents because the shadow price remains unchanged because the increase is 5. And you could increase up to 625 before the shadow price will change. So that's why we could use it to re-evaluate the total cost as the old one plus the additional due to the constraint increase. Okay. Here is example number 2. Currently, Sarah is allowed to work up to 25% of the senior hours. Okay. Now, the constraint now is changing because management has decided to take away 1 hour of this permission, take it away 1 hour away from the 25% of the senior hour and allow Sarah to work less. What will happen to the total cost? They want to use this hour that Sarah is assigned now to this project take away 1 hour from here and maybe assign it to another project. her into another project. What will happen to the cost here? So you look at this constraint, you say, what is changing? This value on the right-hand side of the constraint now becomes the same value minus 1. So you reduce what is the value here, minus 1. Right now we have a 0, so it becomes negative 1. What will be the effect on the total cost? First, you want to see if the shadow price is changing. Negative 7.2 is the shadow price. You can drop it by 625 on the right-hand side before the shadow price is changing. But you drop it only by 1. So the shadow price can be used. What happens then to the total cost? Take a look here. The new total cost will be the old one, which is 37.80, plus the change due to the right-hand side changes, and it's negative 7.2 on the shadow price, times negative 1, because that's what happened to the right-hand side. And you see an increase of the total cost. So you took away an hour from what you allowed before to Sarah, and now she is not going to work the last hour. In fact, she was working the last hour. If you notice, 30 hours is exactly what she is working now. And now she will not be able to work the last hour. This will cost $7.20 more for the project, which means her hours are beneficial for the company. So when they see this, and when they see a negative shadow price on the situation like this, they might change their decision to take away this hour. In fact, what if they decide to give Sarah another hour above the 25%? I'm looking at this constraint, okay? I'm looking at the allowable increase, and it's 150 hours. Every hour that you add to Sarah here will save the company $7.20. So I'm taking you back to the definition of shadow price. It's the change in the objective function per 1 unit increase on the right-hand side. If I'm adding Sarah 1 hour more to work here, then we are saving $7.20. And we are sure to assign this hour to her, because that's how you get the saving. So management can learn a lot from such results. And if you have many constraints and many workers or many groups of workers, and you see shadow prices, this teaches you a lot on where do you want to give more resources, or where do you want to make it more tight, and compare. What if you take away an hour from Sarah? Then you pay $7.20 more, but the same hour when she's working in another project, you are gaining $10 an hour. So on the balance, you want to make this change. So this is how you can make decisions with shadow prices, and that's why I keep coming back to it, because it's important to understand the concept. So this was about Sarah, and just let me look at the time. Yeah, okay, we are good. We are very good. There are 2 more questions that I am adding here. Actually, these are questions that appear in the original problem. This is problem number 6 in your text. So here's the question. Lisa could be assigned more than 50 hours. Lisa right now is assigned up to 50 hours. And the reason was, the story is that she is a very busy girl and she is involved in many other projects. So they didn't want other projects get hurt. They limited the time that she can spend on the new project to 50 hours. Now, suppose Lisa could be assigned more than 50 hours. What effect would this have on the optimal solution? Okay. Which value is changing? As I said, this should be 50 here. So now let's say it becomes 51, 1 hour more. Well, common sense, first of all, how many hours of the 50 allowed to her here I've been using? Only 48. So the last 2 hours, it's called a slack. I didn't use them. So they don't cost the company anything. The cost is 0 of the last 2 hours. So if it's optimal right now to not assign her to 50 hours, why would I assign the next 3 hours if I add 1 hour? Right now, I'm not using even 50. This tells you why the shadow price is 0. Because 1 hour more added to Lisa will not be used anyway. And the shadow price of the last 2 hours is 0 because you don't use them. So the current solution that assigns 48 hours to Lisa will not change. So when you see a 0 shadow price and you make a change within the range, the shadow price will remain 0 and the optimal solution in this case will not change. So neither the total cost will change because the shadow price is 0 and the optimal solution will not change. When a constraint is not binding, when is it binding? When the right-hand side equals to the left-hand side, because for example, this one, you are using all the 150 hours. So give me another hour, I'll do better. But this one is not binding. It's 48 against 50. When you see such a constraint, the shadow price will be 0. And if you are changing the right-hand side within the range allowed, the solution will remain the same. And the objective function will remain the same. So that's what I was explaining here. Okay. And now a second question now. This was a second question now. If Sarah were not required to work minimum number of, just a moment. If Sarah, minimum number of hours, she is assigned here to not less than 15% of the total hours. That's what Sarah is doing. And 30% here is more than 15%. We saw it before, it was 20%, 20 hours. So now, no, 22.5 was the 15%. She is assigned to 30 hours. Now the question is, what if, what if she was not required to work minimum number of hours? Would the optimal solution change? So if there was no limitation below her current assignment, what would it mean? It means that this constraint would disappear. You don't have such a constraint at all. Would the total cost change if you just take away this constraint? The constraints say Sarah should not be less than 15% of the total hours. 15% of the total hours, 22.5 hours. She was found to be assigned to 30 hours. Then you don't have to limit it as 15% because she is assigned to more than that. It's similar to what Lisa did, only on the other direction. So if you take away this constraint, what does it mean? You write 0 here, Sarah is greater than 0, instead of Sarah is greater than 15%. When you write Sarah is greater than 0 as a constraint, you actually eliminate the constraint because Sarah is going to be assigned to 0 or more anyway. It's not even a constraint on the problem. So you eliminated the lower bound on how much Sarah can be assigned to. And now you ask then, what is the change I made in the model? A constraint that was 22.5 on the right-hand side here now becomes, oh, the lower decrease is infinity. So it can drop to 0. I can eliminate the value 22.5. This is falling inside the range. and still have a shadow price of 0. So eliminated the constraint does not cost any change in the total cost for the same reason that adding time to Lisa didn't cost any change. So it's just the same example of 0 shadow price that will guarantee that this solution will remain the same and Sarah will still be assigned to 30 hours and 72 and 48. All this will remain optimal, no change at all in the total cost. So other than one more concept that I still contemplate of adding to you, not today, on sensitivity analysis, this is what you need to know when you do linear programming. So in linear programming, what I would like you to be able to do to set up the linear program as we did on the PowerPoint. That's on a piece of paper, write down a linear programming model. Do not worry about Excel at all. And then take this model, translate it into an Excel spreadsheet, translate this one into a solver model, solve a problem, obtain sensitivity analysis, and then answer sensitivity analysis questions. That's the sensitivity analysis that I would like you to know. And what is left for us now is to go to other types of linear programs. And the next one is called a blending problem. Blending problem is doing the opposite of what we did in all the problems so far. For example, remember we had a finance example in which we tried to optimize a portfolio of a bank giving loans, trying to maximize the total return. So the bank has a budget, it was a resource, and the question was how to split the budget among 3 types of loans. Split is the word. Then we had a marketing example in which you had budget and then you have different media. So we had newspaper ads and then you have radio ads. And the question is how to split the budget among these 2 in order to maximize exposure. Many of the linear programming problems are about overall resources being allocated to different activities. The blending problem, which is very popular in linear programming and optimization in general, is doing the opposite. You take resources, you mix them in order for the product or products come out with required qualities at minimum cost, say. I'll give you one such example. Hospitals are building diets for their patients, say after surgery. And the diets need to include vitamin A at a certain amount daily recommended, vitamin C and calories, protein, not more than amount allowed of cholesterol, not more than amount allowed of fat. The diet has to meet many requirements. You can build the diet by mixing different foods that the hospital has to purchase at different costs. Each food has an amount of vitamin A, an amount of fat, an amount of cholesterol. Each one is different. Question: how do you mix those foods into a diet that meets the required qualities at minimum cost? It's called the diet problem. It's a blending problem. Of course, when you do that, that's between the 2 of us, you don't think about taste. So you bring a chef that will cook it for them, so the patients will eat something, and it will be still nutritional. But these are examples also in the drug industry, where you mix different chemicals in order to create a drug that has to meet certain requirement by the FDA. And the question is how best to do it at minimum cost. It's very popular in the petroleum industry, in which you have crude oil from different wells, and they have different qualities. Now you have to mix them and to create different products. Texaco has been doing it for years now. From the early 50s, they reported billions of dollars saving because they found a good way of doing it. So you mix different unprocessed oil products and process them and create product that they sell then to customers. But this product has to have octane. Octane is the main thing, but it's not the only thing. And we'll have such an example later, you'll see. We are going to mix different products to make, by the way, the blending problem, also called a mix problem, food mix problem, for example, would be in the farming industry when you mix different kind of foods for cows, for example. You create diet for cows, so they call it food mix. But it's blending, it's just like here. So I want you to see a simple problem on the blending problem. It's really simple. It's by design very simple. And it's not the one from your text. The second problem that I'll do next time will be from the text. Same nature, only have more features. So here you have a producer who is buying ores from Bolivia. That's what the original problem. One ore is called La Paz ore, and the other one, I forget the city. It's coming from the two different mines. And because it's coming from different mines, the amount of copper, zinc, and iron and the amount of waste in each one is different. The cost of each one of those ores per 100 pounds is also different. Everything here is the amount in pounds per 100 pound of ore. So for example, ore one is providing you with 20 pounds of copper in each 100 pounds of ore. If you add all those values, you get 100. So that's how many pounds of zinc, of iron, and of waste that you are having in 100 pounds of ore one. Now, the company knows they've signed a contract and they have to sell, to provide by the contract, 800 pounds of copper, 600 pounds of zinc, and 500 pounds of iron. Just as a comment, because of the way it is going to be formulated, we have to add a comment that say, this is what they have to provide by the contract, but if they happen to produce more of one of these minerals, they can sell them in the free market for the same price that they will sell by the contract. Now, this is not always true. Sometime in the free market, they will sell it for more than what they sell it in the contract, because in the contract, they guarantee sales, so they give discount to the buyer. But in the free market, they will charge more. So then you have to add this feature to the model. We don't have it, it's simplified. They have to produce 800, 600, and 500 at least. And if they produce any more of those, of these same minerals, they can sell it for the same price. Okay, so now, how do you formulate the problem such that the total cost for TRP is minimized? Because they purchase it. So here's the situation. They buy an amount of ore1 and ore2, and then they blend it. When they blend it, they will get amount of copper here that has to be more, at least 800. When they blend the amount of zinc, that has to be more than 600, and so on. So the question is, how much ore1 and ore2 to purchase, minimize your cost, and still meet your constraints? Here are the variables. ore1 and ore2 will represent the amount of blended of each ore in 100 pounds, because this is our unit. And then we try to minimize cost. You see the objective function. It's 100 times ore1 100 is the cost per 100 pounds of ore 1. And here are the constraints. So the amount of copper in the blend is the sum of two amounts. One is what you gain from ore 1. So you, on each 100 pound, you have 20 pounds of ore 1. So 20 times how many hundreds you get from of ore 1, and here you get at least 800. And all the three constraints have the same logic. And this is the model. Now to solve it, I just need to see if you have time. We have time. I'm going to the Excel. We'll get the solution, and maybe we even can look at the sensitivity analysis of it, because I don't want to start the new problem that it's in the next slide. So I'll go out here. And in the next slide, yeah, I'll start a new problem. So I don't want, I'll go to Excel again. Okay, I'll go to Excel again, and this time it will be here. It's a different file. Both will be online. Both problems will be online. But for now, I'm using only one Excel link. Okay, so this is the problem. You see it here. If you read a problem, everything is provided to you here. See, the problem is provided to you here, and the actual problem is here. Okay. We saw the model before. Notice that in this model, I don't have to add zeros and ones to fill in the coefficients for all the variables, because there are coefficients already. These are the original coefficients in the model, so I'm just using them. Now, the sum product here cover these two variables and these two coefficients. Here it is, see? And all the sum products are the same here. So I'm going to solver now. I'm going to solver. And take a look. M3 is our objective, and K2 to L2 are here, the two variables. And the constraints, all of them are greater than or equal to. So I added all of them in one hit. I didn't have to do it 3 times. I highlighted M, let's see, which M is it? M5, M5, M6, MA7 is greater than or equal to 05, 06, 07. Then I solved the problem. I checked to see simplex and non-negativity, of course. Here is the solution. And here's the sensitivity report. So the sensitivity report will be, oh, wait a minute. It took me to the previous spreadsheet. I have to be here. Blend 1, and here's the sensitivity report. So I'll go there in a minute. What do you see here? Here is the blending plan, 20 hundreds, which is 2,000 pounds of ore 1 with 10,000 pounds of ore 2. That's the blend. If you do that, your cost is minimized at $3,400. See? You know what was not considered here at all? How much is the supply for ore 1? How much is the supply from ore 2? Each one coming from a different mine. Maybe this mine cannot give me more than 18 pounds. There is a capacity issue. So this will be part of the formulation in the next problem. So the sensitivity report that I want you to see here is here. I didn't put it on PowerPoint, so pay attention here. Here is the optimal solution. See, here are the constraints right-hand side and left-hand side. Okay. The values here tells you how much 100 can increase or decrease before this optimal solution is changing. And this is something which is quite interesting. You can add 80% to the cost of R1 up to 180, and you still will be ordering the same amount. It becomes way more expensive, but you will still order 20 by 10. It can drop by 30% to $70. You will still order the same. You will not order more here. Not because you reached the maximum capacity, because that's optimal economically. And so this is what you can learn from this for management to know how much they can negotiate prices, for example. Then comes here. You see, we don't have the problem with zeros here, and I tell you why. A model that has percentages, like in the Lisa, Sarah, David problem, we had percentages on the right-hand side, then you will see zeros on the right-hand side, and this is kind of sometimes confusing. But here, all the constraints are constants, they remain constant, and here's what you find. Copper, you have to produce at least 800 pounds of copper, and that's what you blend. You are getting 800 pounds. This constraint is called binding. This constraint here, it's non-binding because you are required to produce 600 pounds, but you produce 650 of the blend. So you have 50 pounds extra on what the contract required. You can sell it in the market, but then what does it tell you? If this contract, say the buyer wants to increase the amount by 10 pounds, he wants 610 pounds. What will happen to the total cost of the blending? Nothing. Because the shadow price is zero, you already are blending more than 600. So if this goes to 610, nothing will happen. The only thing that is happening here, and a surplus of 50, that's what it's called in the language, surplus. Surplus of 50 becomes a surplus of 40 because now you have to fill in 610 and not 600. But at no extra cost to you. If, for example, 500 pounds of iron were dropping to 20, by 20, so to 480 pounds, you could save on the total blending cost $2 times, okay, let's see. What is this 2? It's the each 100 pound, no, each pound added to the contract will increase the cost by $2. But if you drop it by 20, you save 2 times 20. Can I use the shadow price? Yes, because the allowable decrease is 100. So this is what you have to look at when you do sensitivity analysis. And as you see, the questions repeat themselves. There is only one more thing that I'll add about it. It will not require any new run, but a new application of the same data here. And that's what I think we'll do on Thursday. Then I want to go to problems called transportation. An assignment you'll do next week. That's what we'll do next week. And it's very interesting. It's quite easy, but very, very interesting. Logistics. It's application in logistics. And with this, I am done for today, unless you have a question. So I'll stop sharing. And yes, any question?
Can I ask about the quiz on Thursday?
Yeah, sure.
Is it going to be during the class period, or are you going to give us?
No. So first I'll have a presentation, but it'll be shorter.
Okay.
And after that, I'll email to you the quiz, and you'll have an hour to return it to me.
Okay.
And as I explained at the beginning, this is the only way I can do it reasonably, because I can't give you the quiz first and wait that you will return it to me and then have a presentation, because each one of you will return it at a different time when I would start. So that's why I needed to do it this way.
Okay.
Okay, so that's it. Any other question, guys? Was clear today? Scream at me if not.
Yeah, I got one more question.
Yes.
So the recording that you did for the Monday, Wednesday class is, would you say it's better than this one, or?
No, I think I'll also upload this one, and so you'll have two of them, but they will be similar, but I think this is cleaner. So okay. You can identify it by the time and date, and that's how you know which one to use.
All right, thank you.
Okay. Any other question? Okay, thank you.
Thank you, Professor.
Okay, bye-bye.
Bye-bye.